There is a place in the universe where all our laws break down, where time as we know it stops, and where space stretches into an infinity we cannot comprehend. It's not a monster, it's not an object, it's a location, a destination, the final destination from which nothing, not even light, can ever return. We call it a black hole, but what truly lies inside? What would you find if you could somehow survive the journey past its edge into the heart of the ultimate unknown? This isn't a story of destruction, it's a quiet voyage to the very end of reality.
Before we cross that threshold, we must understand what we're looking at. Forget the images of cosmic vacuum cleaners sucking up everything in their path. A black hole is far more subtle, far more fundamental. It is the natural endpoint for the most massive stars in our universe. It is gravity in its purest, most extreme form. An object so dense it has punched a hole in the very fabric of space-time. If you find your mind drawn to these quiet explorations of cosmic mysteries, consider subscribing. We have many more voyages planned to the edges of understanding. Our journey begins with a life, not a death. The life of a star, many times more massive than our own sun. For millions of years, this star is a perfect balancing act. In its core, a furious engine of nuclear fusion crushes atoms together, releasing incredible amounts of energy. This energy pushes outwards, a constant pressure fighting to blow the star apart. But an even greater force pulls inwards, gravity. The star's own immense mass trying to crush it down to a single point. For its entire life, these two forces are locked in a perfect cosmic stalemate.
But this balance cannot last forever. The fusion engine requires fuel, and eventually, the star begins to run out. It starts burning heavier and heavier elements, a desperate attempt to keep the fires lit and the collapse at bay. It swells into a red supergiant, its outer layers expanding into the cold of space. But the core is losing its battle. The outward push of fusion weakens second by second, and the inward pull of gravity, which has been patient for millions of years, never wavers. It is relentless.
And then it happens. The star fuses its last atom of fuel. The outward pressure vanishes in an instant. With nothing left to hold it back, gravity wins. It wins absolutely. The core of the star, a mass millions of times greater than our Earth, collapses in on itself in a fraction of a second. The implosion is so fast, so violent, that it triggers a shockwave of unimaginable power. This shockwave rips through the outer layers of the star, blowing them away in one of the most brilliant events in the universe, a supernova. For a few weeks, this single dying star can outshine an entire galaxy. It seeds the cosmos with the heavy elements that will one day form new stars, new planets, and perhaps new life. But this spectacular death is just a distraction. It's the shroud covering what was left behind. At the center of that fading, ghostly cloud, the collapsed core continues to crush itself past any point we can describe with our current physics.
This is where the black hole is truly born. The core has become so dense that its gravitational pull is inescapable. It has created a boundary around itself called the event horizon. This is not a physical surface. You could pass through it without even knowing. It is simply the point of no return. Imagine it as a river speeding up as it approaches a waterfall. At some point, the water is moving faster than any boat could paddle. The event horizon is that point for space-time itself. It is flowing into the black hole faster than the speed of light. Since nothing can travel faster than light, nothing that crosses it can ever get back out.
Here, we encounter our first great paradox, courtesy of Einstein's theory of relativity. Let's imagine you are in a ship falling towards the event horizon. From your perspective, you cross the boundary at a specific moment and continue on your journey. But to someone watching you from a safe distance, something very strange happens. As you get closer to the horizon, your ship appears to slow down. The intense gravity stretches the light waves coming from you, shifting them towards the red end of the spectrum. You would appear redder and redder, slower and slower, until you seem to freeze at the very edge, your image smeared across the horizon for all eternity. They would never see you cross.
So which reality is true? Yours or the distant observers? The strange answer is both. Reality is relative. The best way to picture what's happening is to stop thinking of space as empty. General relativity tells us that space and time are a single, unified fabric, space-time, and massive objects warp this fabric. A black hole doesn't just sit in space-time, it creates a current, a flow. The event horizon is the point where this flow becomes faster than light. You are not so much falling into a hole as you are being carried by a river of reality itself over a cosmic waterfall.
Just outside this point of no return, there exists a region of pure strangeness. It's called the photon sphere. Here, gravity is so strong that photons, particles of light, can be forced into orbit. Imagine a beam of light trapped, chasing its own tail in a perfect circle around the black hole forever. If you could stand on this sphere and look straight ahead, you would see the back of your own head, as the light from it has traveled all the way around the black hole to return to your eyes. This ring of trapped light is one of the last features of our familiar universe before we take the plunge. So let's do it. Let's cross the event horizon. What does it feel like? For a small stellar mass black hole, the experience would be unpleasant. The tidal forces would tear you apart long before you reached the edge. But for a supermassive black hole, millions or billions of times the mass of our Sun, the story is different. The event horizon is much farther from the center, and the curvature of space-time is gentler. You could, in theory, drift across it without noticing a thing. One moment you could escape, the next you cannot.
The sky in front of you would still look normal, but the sky behind you would be gone. You have passed through the one-way door.
Inside, your quiet voyage is about to get strange. Even if you cross the horizon of a supermassive black hole safely, your doom is still inevitable. It has a name that sounds almost comical, but the reality is anything but. Spaghettification. It's the result of tidal forces. The gravitational pull at your feet, being slightly closer to the center, is exponentially stronger than the pull at your head. This difference in force would begin to stretch you, gently at first, then with more and more power. You, your ship, every atom of your being would be elongated into a thin stream of particles flowing down towards the center.
But something even more profound is happening to the nature of reality itself. According to the mathematics of relativity, once you cross the event horizon, space and time swap roles. Think about it. In your normal life, you can move freely in the 3 dimensions of space, forwards, backwards, up, down, but you can only move in one direction in time, towards the future. Inside a black hole, this is reversed. The path to the center, the singularity, is no longer a direction in space. It becomes the future. You can no more avoid hitting the singularity than you can avoid next Tuesday. All paths, all possible futures lead to that one single point.
And what is this point? In classical physics, in Einstein's theory, it's called the singularity. It is the end of the line, a point of 0 volume and infinite density. All the mass of the collapsed star and everything that has ever fallen into the black hole crushed into a region smaller than an atom. Here, all the known laws of physics, including relativity itself, break down completely. They produce nonsensical answers, like dividing by 0. The theory that led us here tells us that this is where it can no longer guide us. It's a dead end, a wall.
Physicists are deeply uncomfortable with infinities. An infinity in an equation is usually a sign that the theory is incomplete. It's a placeholder for a piece of the puzzle that we're missing. Nature doesn't seem to do infinite. So while the classical singularity is a mathematical certainty in general relativity, most physicists believe it's not the true answer. Something else must happen at the heart of a black hole, something that our current understanding just can't see. To find that something, we need to bring in the other great pillar of modern physics. That pillar is quantum mechanics, the science of the very small, the rules that govern atoms, electrons, and all the particles of the subatomic world. General relativity is a beautiful theory for the very large and massive, like stars and galaxies. Quantum mechanics is the reigning theory for the very small and energetic. The problem is, these two theories don't agree. They speak different mathematical languages. And the singularity of a black hole is the one place in the universe where both theories must apply. It is both incredibly massive and incredibly small. It is the ultimate battleground for physics. So what happens when you apply quantum rules to the singularity? The idea of a single, infinitely small point begins to dissolve. At the quantum level, reality is fuzzy and uncertain. The Heisenberg uncertainty principle states that you cannot know both the precise position and the precise momentum of a particle. This principle might prevent space-time from ever collapsing to a true point. Instead of a singularity, you might find a region of quantum foam, a chaotic, bubbling storm where space and time lose all meaning, constantly fluctuating in a state of pure probability. One attempt to unite these two theories is string theory. It proposes that at the most fundamental level, everything is made of tiny, vibrating strings of energy. In this view, there is no singularity. Instead, the collapsed star and everything that falls in becomes a tangled, messy ball of these strings, a fuzzball. A fuzzball has a definite size. It's not a point of infinite density. It doesn't even have a true event horizon in the classical sense. The surface is blurry or fuzzy. Information that falls in isn't destroyed at a singularity. It's just woven into the complex vibrations of the fuzzball. Another leading contender is loop quantum gravity. This theory suggests that space-time itself is quantized, made of fundamental, indivisible building blocks, like pixels on a screen. You cannot have a space smaller than one of these loops. So, as the star collapses, it can't shrink to an infinitely small point. It reaches the smallest possible size and can be compressed no further. The immense pressure causes it to rebound. Some physicists believe this creates a Planck star at the heart of the black hole, a hyper-compressed object that will eventually bounce back, perhaps in the far, far future.
This idea of a bounce leads to one of the most tantalizing possibilities. What if the singularity isn't an end, but a beginning, a gateway? This is the idea of a wormhole or an Einstein-Rosen bridge. Perhaps the collapse doesn't stop, but punches through space-time, connecting our universe to another. Or maybe it connects to a different point in our own universe, far away in space and time. In this scenario, the black hole is one end of a tunnel, and on the other side is a white hole, a theoretical object that spews out matter and energy, but which nothing can enter.
While mathematically possible, white holes are considered highly unlikely to exist in our universe. They are incredibly unstable. The slightest bit of matter falling towards one would cause it to collapse into a black hole instantly. And we've never seen any evidence for one. So while the idea of a wormhole is a staple of science fiction, most physicists believe these bridges, if they can form at all, would be so unstable and chaotic that nothing, not even a single particle, could pass through them intact. There is an even grander idea, though, a theory called cosmological natural selection. It suggests that when a black hole forms and collapses, the singularity it creates could trigger a new Big Bang, creating an entirely new universe inside the black hole, but disconnected from our own, a baby universe. In this model, our own universe might have been born from a black hole in another parent universe. It's a staggering thought that these dark, silent objects scattered across our cosmos could be the seeds of new realities.
All these theories are attempts to solve a very deep problem, one that troubled the great Stephen Hawking for years. It's called the black hole information paradox. A fundamental rule of quantum mechanics is that information can never be destroyed. It can be scrambled, like burning a book. The information in the ink and paper is converted into smoke and ash. But in theory, you could piece it all back together to reconstruct the book. But a classical black hole seems to violate this. If you throw the book into a black hole, it falls to the singularity and is crushed out of existence. The information is gone forever. This, to a physicist, is a crisis.
Stephen Hawking provided a partial answer, and in doing so changed our understanding of black holes forever. He proved that they are not completely black. By applying quantum mechanics to the edge of the event horizon, he discovered that black holes must radiate energy. They glow, ever so faintly, with what we now call Hawking radiation. This means that black holes are not eternal prisons. They evaporate. How does this happen? According to quantum theory, empty space is not empty at all. It's a sea of virtual particles constantly popping into existence in pairs, a particle and its antiparticle, before quickly annihilating each other and disappearing. This happens everywhere in the universe, all the time. But when a pair of these virtual particles pops into existence right at the edge of an event horizon, something different can happen. What happens next is one of the most profound and unsettling ideas in modern physics. Occasionally, one of these virtual particles will materialize just outside the event horizon, while its twin appears just inside. They're born straddling the point of no return. The one inside is immediately captured, dragged inexorably toward the singularity. It's gone forever. But think about its partner, the one left outside. With its twin gone, it can no longer annihilate. It's been orphaned at the moment of its birth. The energy it borrowed from the vacuum of space can't be paid back in the usual way. So it gets promoted. It becomes a real, tangible particle and escapes out into the cosmos, a ghost made solid. Now, step back and consider what this looks like to an observer far away. They can't see the quantum dance happening at the horizon. They can't see the virtual pair or the particle that fell in. All they see is a steady stream of particles, photons, neutrinos, all sorts of things, radiating away from an object that's supposed to swallow everything. It looks as if the black hole itself is glowing with a faint thermal heat. This immediately presents a paradox. The universe has strict accounting rules, the most important being the conservation of energy. Energy can't just be created out of thin air. So where did the energy for that escaping particle come from? The answer lies with its doomed twin. To balance the cosmic books, the particle that fell in must be considered to have negative energy. It's a sort of energy debt. By falling into the black hole, it pays the price for its siblings' freedom. And when that negative energy is added to the black hole's total positive energy, the sum goes down. Because of the direct relationship between energy and mass,
E equals mc squared, this subtraction of energy effectively subtracts a tiny, tiny amount of mass from the black hole. With every particle that escapes, the black hole pays a toll. The black hole gets ever so slightly smaller. It evaporates. Now, when we say this process is slow, our minds can't really grasp the timescale we're talking about. It's a process that fundamentally redefines what the word long even means. Let's try to put it in perspective. For a black hole with the mass of our own sun, the time it would take to completely evaporate is a 1 followed by 67 zeros. The current age of the universe? That's a 1 followed by a mere 10 zeros. So for a solar mass black hole to radiate away a tiny fraction of its mass, say the mass of a single mountain, would take longer than all of cosmic history has existed so far, multiplied many times over. And that's a relatively small black hole. What about the supermassive giants at the hearts of galaxies? Because the evaporation rate is inversely proportional to mass, the bigger they are, the colder they are, and the slower they die. A supermassive black hole would take trillions of years to disappear, a number so large it's functionally infinite to us. You have to imagine a future universe so deep in time that it's almost perfectly empty and cold. The last star will have faded trillions of years before. The galaxies will have dissolved into a diffuse cold gas. There will be almost nothing left. In that profound, silent darkness, these black holes will be the only structured things remaining. They are the final embers of reality, glowing with an unimaginably faint warmth, the very last holdouts against the final, absolute cold. They are the universe's last act.
But what happens at the very end? As the black hole shrinks, the rate of evaporation speeds up. In its final moments, a black hole that has existed for eons will release all its remaining mass in a final, brilliant flash of energy. A silent, lonely firework in the dark, signaling the end of one of the universe's most mysterious objects. But this raises a question. If the black hole evaporates, what happens to the information it contained? Does it leak out with the Hawking radiation, scrambled but intact? Or is it truly lost forever? The paradox remains.
Even the idea of information leaking out has its own problems. Some physicists argue that for the information to escape, it would require breaking the quantum entanglement between the particles falling in and the particles escaping. The energy required to break this link would create a firewall at the event horizon, a wall of high-energy particles that would incinerate anything attempting to cross. This would mean our gentle, unnoticed crossing is impossible. You wouldn't fall in, you would be destroyed at the edge. This contradicts Einstein's theory. It's another deep conflict at the heart of physics. While we puzzle over their interiors, we cannot forget the vital role black holes play in the cosmos we can see. At the center of almost every large galaxy, including our own Milky Way, resides a supermassive black hole. They are not just cosmic oddities, they are galactic anchors. Their immense gravity helps to hold the galaxy together. Their feeding frenzies, when they consume gas and stars, can regulate star formation across the entire galaxy, acting as a cosmic thermostat.
For all this theory, for all this mathematics,
You might wonder if we've ever truly seen one, and the answer, astonishingly, is yes. Using a network of telescopes as large as the Earth itself, astronomers were able to capture an image of the shadow of the supermassive black hole at the center of the M87 galaxy. We cannot see the black hole itself, but we can see the silhouette it casts against the glowing, superheated gas of its accretion disk. It is a direct observation of the point of no return, a quiet, blurry image that confirms Einstein was right, at least about the outside.
So, what lies inside a black hole?
The honest answer is, we don't know. We have reached the absolute frontier of our knowledge. It could be a point of infinite density, as relativity suggests. It could be a quantum fuzzball, a bouncing Planck star, or a gateway to another universe. To truly know, we would need a new theory of everything, a theory of quantum gravity that can finally unite the world of the large with the world of the small. The black hole is not just an object, it is a signpost pointing the way towards the next great revolution in physics. Perhaps the journey inside a black hole is not one that can ever be taken physically. It is a journey of the mind, a thought experiment that pushes our theories and our imagination to their absolute limits. In trying to understand this place of ultimate darkness, we shed more light on the nature of space, time, information, and reality itself. The black hole acts as a cosmic mirror, reflecting the boundaries of our own understanding. Our sleepy voyage to the edge of reality must end here, on the outside looking in. We have traveled from the death of a star to the birth of a mystery, from the certainty of Einstein to the probabilistic haze of the quantum world. We are left not with answers, but with better, more profound questions. The black hole doesn't give up its secrets easily. It simply waits, silently, holding the key to the ultimate nature of our universe within its silent, dark heart.
So now, the question goes to you. After this journey, what do you think lies inside? Is it a singularity, a gateway, or something stranger than we can possibly imagine? Let us know your thoughts in the comments below. What cosmic mystery should we explore on our next quiet voyage?